video, let us see gravitational potential energy. Gravitational force is a conservative force. A force is said to be conservative if the work done is independent of the path. Now here there is a mass m1 fixed and m2 is to be moved from a position whose distance is r dash to r dash to r. First let us find the work to be done during this infinitesimal displacement dr. Now mass m2 is at a distance r from m1 and then this 2 points, distance between these 2 points is dr. So during this infinitesimal displacement, work to be done is f vector dot dr vector, external force. We are moving with a constant velocity, so external force will be equal to the gravitational force. The magnitude of the external force should be equal to the magnitude of the gravitational force. So the gravitational force is given by this relation G m1 m2 by r square. So this is the magnitude of the gravitational force. The external force to be applied is equal to the magnitude of the gravitational force. Now we can substitute for this G m1 m2 by r square, then r cap. This is a small amount of work done dw during this infinitesimal displacement. Now substitute for this, then this is the magnitude of the force, then it is acting along the line joining the masses, so it's the r cap. So this vector can be written dot dr vector. But for dr vector, we can write dr into r cap because the magnitude of the dr vector is dr. Now r cap dot r cap is 1. It's a unit vector. Dot product of r cap dot r cap is 1. So it can be written like this: G m1 m2 by r square dr. R cap dot r cap is 1. Then total amount of work done is got by integrating this expression. So work to be done to move from r dash to r. So the lower limit is r dash, upper limit is r. Now G m1 m2 you can take outside, then 1 by r square dr. Then 1 by r square can be written as r raised to minus 2. Then we have to integrate it. So when we integrate it, use the integration formula. Integral of x raised to n dx is x raised to n plus 1 by n plus 1. So minus 2 plus 1 and n plus 1. Minus 2 plus 1 minus 2 plus 1. After the integration, apply the limit r dash to r. So this is the work to be done to move the mass from a position r dash to r. Work done is equal to G m1 m2, then r raised to minus 2 plus 1 divided by minus 2 plus 1. Limits r dash to r. Then minus 2 plus 1. So minus 1, minus 2 plus 1, minus 1. Take this minus 1 outside. So it can be written minus G m1 m2. Then r raised to minus 1 can be written as 1 by r. Then you apply the limits r dash r. So upper limit is r minus lower limit. Next you remove this bracket. Minus G m1 m2 by r minus, then take this inside, minus G m1 m2 by r dash. So this is the potential energy of a system of masses m1 and m2 when it is separated by a distance r. So this can be written as ur. This is ur minus this is ur dash. This is the potential energy when it is separated by a distance r dash. So work done is equal to change in potential energy. This is a potential energy at a distance r. This is a potential energy at r dash. Now two cases. R dash is greater than r. R dash is greater than r. You are moving m2 closer. Then because of the attractive force, m2 will move by itself. So no work is done by external force. So work done is said to be negative. When r dash is greater than r, when this r dash is greater than r, you are dividing by a bigger number. So without this minus sign, when we consider, when you divide by a bigger number, it is going to be lesser. But there a negative sign is there, so it is going to be bigger than this. So a smaller number minus bigger number. So it is going to be negative. Work done is negative. Second case, r dash is lesser than r. That means you are moving away. Then in this case, work done by the external force is positive. Then we are interested in the potential energy difference. So for reference, we can take r dash to be infinity and potential energy at infinite distance will be 0. This will be 0. When r dash is infinity, this term will be 0. Now work done is minus g m1 m2 by r, because this term is going to be 0. Now the work done can be written as, this is potential energy when it is at a distance r, minus, when r dash is infinity, we can write potential energy when it is at infinite distance. So gravitational potential energy of a system of two masses separated by a distance r is equal to the gravitational potential energy difference when the masses are separated by a distance infinity and when masses are separated by a distance r.